So the convection ultimately is going to be part of the energy transport from the tropics to higher latitudes and from the surface to the upper atmosphere, right? So eventually we have to come back to the energetics of these convective motions. So let's add energetics to this simple model we've been using so far. And it basically comes down to converting between potential energy and kinetic energy. Kinetic energy is the motion of the fluid, the winds, and so on. And potential energy is the relative amount of energy you have because of your buoyant position or elevated position beyond your stability point, and so on and so forth, right? In an intuitive sense. So let's think about that profile we've been looking at here, right? We had ρ1 at z1, ρ2 at z2, and the initial potential energy of the system in a simple way can be written as g times ρ1 z1 plus ρ2 z2. This is the total potential energy of these two parcels, and when we moved them and exchanged them, then we converted the potential energy to ρ1 z2 plus ρ2 z1 because we displaced them. Then we have to see how the potential energy changed because of this displacing the parcel. So PE final minus PE initial, in this case, you can just do the simple calculation. Minus G times ρ2 minus ρ1 times Z2 minus Z1, which is approximately equals minus G times d rho dz times delta Z, which is what we had done before, right? So it's a very simple way to look at how the potential energy of the system is changed by displacing the parcels up and down respectively. Okay, so in this case d rho dz is of the environment is simply ρ2 of minus ρ1 because those are the environmental densities at the two locations divided by z2 minus z1, remembering that z2 minus z1 delta z is small enough for this relation to be valid. So what are the stability criterion then in terms of the d rho dz? We again look at buoyancy, positive, neutral, negatively buoyant, if d rho dz is greater than 0, equals 0, less than 0 as we saw before. And we saw it in terms of temperature, where we called it stable, neutral, and unstable. So in that case, dt dz is less than 0 for an unstable situation, equal to 0, no temperature gradient for neutrally stable, and stable for dt dz greater than 0. Okay, so in the lab, the book provides a beautiful example of how convection can be set up. There is a heating pad at the bottom. There is some potassium permanganate put in to make the flow visible. There is a mixer at the top to prevent diffusion and mixing, okay, of the hot and cold waters to maintain some kind of stratification. And the initial temperature profile is this TEZ, so you are warming at the so let's see, heating pad. So you have initially you have you have introduced lighter water at the top and heavier water at the bottom, so it's colder temperatures and warmer temperatures. And once you start heating, you're going to set up convection. So you can see this convective motion shown here where water rises and colder water has to sink. So if it is done without creating a lot of turbulence and mixing, then you should see these nice loops. It's like tomato soup, I think, can provide you a good Rayleigh-Benard convection cells because it's not viscous enough and can provide good visualization. So what does convection do? Basically, it mixes the warmer and colder waters and creates a profile that is stabilized. That's what convection does. You have instabilities creating a potential density gradient, let's say, and that instability is released into kinetic energy, which is the motion of the convection. Okay, so we will see that there will be overshoots. So this water is going to go into the stable layer and create a inversion. And this happens in the real world as well, as we will see later on. So here they are showing the temperature profile evolving with time at different depths. So you can see cold at the bottom to top, warm at the top, nicely stratified when you started. The heating pad is turned on at some 150 seconds, and you can see that the bottom waters are getting warm. The other waters are also getting warm but slower, so this is warming faster. Next, this one catches up, and you can see these wiggles here, right? So the water column is stabilized and mixed up. The stratification disappears by the time you reach 1500 seconds, but you can see that there is overshoots. So in the book there is actually a figure of the overshoots and the gravity waves that get created, which means what? If the lighter fluid goes beyond its neutrally stable buoyant position, then gravity is going to pull it back, then it's going to overshoot, and it's going to have this little oscillation. Why? Just because when it's moving up due to instability, it's got a velocity that's too fast for it to stop as soon as it reaches its neutrally buoyant position. So it's going to overshoot and come back and then oscillate a little. Why is it called a gravity wave? I think you know that because for creating a wave you need a perturbation, a force. So if you push something, it may not come back unless there is a restoring force, right? So if gravity is the restoring force, then we call it gravity wave. That's why it's called gravity wave. So if you overshoot your neutrally stable position, then the gravity is saying, wait a minute, you have to come back. So that's what creates gravity wave. Okay, very common in the real world, as we will see later on. We'll derive a little expression for gravity wave, and we will look at real world gravity waves.